Welcome. Today we're going to be looking at the accessory structures of the integumentary system. And just as the name suggests, accessory structures are something that complement the skin, just like jewelry would complement your clothing. Reference pages 176 through 180.
There are three accessory structures to the skin: hair, nails, and glands. All of these are formed from epidermal cells, and we'll see how that occurs very shortly here. When skin gets injured or burned, it can heal only if these are undamaged. And we'll take a look at that a little bit later on. The first that we'll look at is hair. Hair has a relatively long lifespan, growing for 2 to 6 years. So one hair can live for 2 to 6 years, which is quite impressive, actually. And I guess I really shouldn't say alive, because hair isn't alive. It's just growing for 2 to 6 years. Once it's done growing, it will stay and not grow for a period of 2 to 3 months before it inevitably falls out. Once a hair does fall out, a new hair starts to form in the exact same location. So looking at our picture over on the right over here, this hair is growing inside of a hair shaft, so to speak. And once the shaft is vacated by a hair, a new hair begins to form. We'll talk about how hair forms a little bit later on in this presentation. But we do lose 20 to 100 hairs per day, meaning that 20 to 100 hairs per day have reached that end of their lifespan, if you want to even call it lifespan. So what happens when hair falls out and a new one does not replace it? Baldness starts to occur, or thinning of the hair. A couple different treatment options for this that people use include Rogaine, hair transplants, and thinning hair supplements. Now, Rogaine is advertised to make hair grow back, and it does that in a relatively small portion of the time, like 10 to 14% of the time. Patients will actually grow hair from hair shafts that no longer have hair. The bigger deal with Rogaine is that the hair that's there stays there longer. So if a hair is supposed to be there for 2 to 6 years, it might be there for like 6 to 8 years. A little bit longer is more of what Rogaine actually does. Then there's hair transplants, which is exactly what you probably think it is. You take hair from one part of your body and you plug it into one of the vacated shafts, and the hair is there, and that works quite well. And then there's also a product called thinning hair supplements. These are conditioners that we'd use in like the shower, and what they do is they make the hair that's there still look thicker and fuller to kind of fill in some of the balding areas. So I guess this wouldn't work on the top of your scalp if you lost everything already and you're just completely bald on top. But if you're starting to thin on the top part of your head, you could use this, and it would make the hair that's still there kind of cover up the areas that have been lost. So hair, it's pretty much always growing. 90% of the 2 to 6 years of the hair is spent in the growth phase, with only a brief period of time where it's not doing anything at all. There's also a couple different types of hair. Grow in the same fashion, same lifespan. One is thick, coarse hair, and other is this very fine, peach fuzzy hair. The peach fuzz hair, that is vellus hair. The thick, coarse hair, that is terminal hair. Once again, they grow in the exact same manner. They have the same lifespan, and they're found all over the body. So how does hair grow? Well, hair grows from a hair follicle, and a hair follicle has a lining in it made up of epidermal cells. These epidermal cells, they operate in a very similar fashion to the stratified squamous cells that we spoke of in our most recent chapter. And if you recall, the bottom layers of the stratified squamous cells were alive, they were boxy in appearance, they could reproduce. And as they would reproduce, the new cells forming would replace the cells above them, pushing each layer upward and upward and upward. And as the cells move upward from the deeper cells reproducing, they would start to flatten out and thin out, and they would get more of the protein keratin that we spoke of. In other words, the cells would keratinize, which would make them stronger, more durable, and in the case of our skin, it would actually make our skin more protective against like UV radiation and outside bacterial cells. Well, in the case of our hair, these cells that have been keratinized and are now dead are actually what form our hair. So the hair that you're touching on top of your head is actually old cells that were inside of our scalp. Now the epidermal cells that are a little bit deeper, that are alive and reproducing, they do need a blood supply, and they get this blood supply at the very, very bottom of the hair follicle through blood vessels found in the dermis. And the blood vessels actually go into the hair follicle through a little indentation called the hair papilla. And we'll see what that looks like on the next slide here. So looking at this image here, we can see the hair papilla down at the bottom here. We spoke of that just a moment ago. And we can see the dermal blood vessels going into the hair papilla to supply the epidermal cells with nutrients. The epidermal cells themselves, that is the purple that we see on either side of the hair follicle. And if you look closely, you can see that the epidermal cells go all the way up the hair follicle, and they're actually existing up here as well. Once again, it's the epidermal cells that, once they divide, go through mitosis, keratinize, and get pushed outward. Those are the cells that inevitably form the hair, which makes its way up to the top of our scalp and makes an appearance. What I'd like you to do is take a look at your integument coloring sheet that we started, and I'd like you to color and label on your paper F, F1, F2, F3, H, and I. Please pause this recording right now so that it doesn't continue to play. Still talking about hair, a little bit different element to it though. We're going to be looking at hair color and what dictates hair color. As you are probably well aware, genes contained within our DNA dictate everything about us, including hair color. Hair color and skin color is determined by a group of cells called melanocytes. Melanocytes produce melanin, which is a pigment. Now there's a couple different forms of melanin that can exist with hair, namely eumelanin or pheomelanin. Now what determines hair color? Well, first off, which type of melanin is present, eu or pheo, and how much melanin is produced from those cells. If an individual's genes produce eumelanin, a person will have darker hair, brown, black, darker. If a person's genes produces pheomelanin, lighter hair, blonde to reddish hair. An individual with eumelanin that has very, very light brown hair will have melanocytes that only produce a little bit of the eumelanin. It will be lighter in appearance. A person whose melanocytes produces eumelanin in heavy, heavy quantities, really dark jet black hair. Same with pheomelanin. If a person's melanocytes produce pheomelanin in very, very light quantities, going to have light blonde hair. If a person's melanocytes produce a lot of pheomelanin, it's going to be darker, and this will be on the red end of the spectrum. And then there's always individuals that have no melanocytes, so these are our albinos. They have white hair, lack of pigment because no melanin at all is being produced. You have this picture in your notes, and although it's not very great or clear, you can definitely get a little bit better picture on the screen here. We can see a variety of different hair colors, dark, light, and everything in between. So what I'd like you to do on your paper is look at several of these, identify which type of melanin is being produced, and if there's a lot of that melanin present, or a little bit of that melanin present, or maybe middle. I'd like you to pause this and look at 3 or 4 of these, identify them by number. You get to choose. You can do 1, 12, 30, 16, whatever you want to do. but please put the number and type of melanin and how much melanin off to the side in your paper, and talk with the neighbor next to you, see what they got. Please pause this video while you do so. Next, we're going to be talking about a muscle that controls our hair, namely our Goosebump muscle, which is the Arector Pili muscle. The Arector Pili muscle is smooth muscle that attaches to the hair follicle. Since it's smooth muscle, it is involuntary. We cannot control it. But it does get stimulated when we get sometimes angry or when we get cold. We can see the Arector Pili muscle right here. It's extending downwards and it connects to the hair follicle. When it contracts, it would make the hair stand up on end. Over here, we can see what it looks like through a side section. We can see that it's connecting once again to the hair follicle. You'll find this on your integument coloring sheet. It's labeled as F6, and there are 2 of them on your sheet. One of them is not labeled. Please color and label the Arector Pili muscle, pausing this video while you do so. The second accessory structure that we're going to be talking about are nails. These are found at the ends of our fingers and toes. They protect the tips. They help pick things up. They help grab things. While there are many parts to the nail, as we can see in this image up here, there's only a few things that we need to concern ourselves with for the purpose of this course. We need to know the nail plate, nail bed, and lanula. The nail plate, that's the actual part of the nail that you can see when you look down. So when you see this person's thumb right here, we can see the nail plate. Underneath the nail plate, if we were to rip out the nail, the cells that you would be touching, the skin you would be touching underneath it, that makes up the nail bed. And this crescent white shaped region at the base, that's the lanula. Both the nail bed and the lanula are underneath the nail plate. So these are epidermal cells that are actively reproducing. They're alive. The nail bed and lanula cells are epidermal, and they do the exact same thing that hair did. They go through mitosis. They push upper layers of cells upward. Those cells start to keratinize as they're pushed upward, and by the time they reach the outermost layer of cells, they're now completely dead and fully keratinized. Those dead keratinized epidermal cells form the nail plate. The lanula, down at the base here, is the most actively growing region of epidermal cells. They go through mitosis at a relatively quick rate. This is what causes our fingernails to be growing outwards rather than upwards. So all these cells in red here, lanula, nail bed, they're all dying, they're all going through mitosis, they're all keratinizing, but these ones up here are going through mitosis at a slower rate than the lanula, pushing the nail plate outward. This concludes this portion of the video. We'll have to pick up with glands on the second one that follows.